Firstly, a very special good morning to everyone present here. Myself, Neha. I am a student of BSc Chemistry Honors Final Year, and today my topic of presentation is the crystal lattices and unit cells. This topic is extracted from the solid state from NCERT. The main characteristics of crystalline solids is the regular and repeating pattern of constant particles. If the three-dimensional arrangement of constant particles in a crystal is represented diagrammatically, in which each particle is depicted as a point, the arrangement is called crystal lattice. Thus, a regular three-dimensional arrangement of points in a space is called crystal lattice. A portion of crystal lattice is shown in figure 1.5. There are only 14 possible three-dimensional lattices. These are called Bravais lattices, after the French mathematician who first described them. The following are the characteristics of the crystal lattice. Each point in a lattice is called the lattice point or the lattice site. Each point in a crystal lattice represents one constant particle which may be an atom, a molecule or an ion. Lattice points are joined by straight lines to bring out the geometry of the lattice. Unit cell is the smallest portion of the crystal lattice which, when repeated in different directions, generate the entire lattice. A unit cell is characterized by first is its dimensions along the three edges A, B and C. These edges may be or may not be mutually perpendicular. Angles between the edges, that is the alpha, beta and the gamma. Thus the unit cell is characterized by the 6 parameters, that is A, B, C, alpha, beta and gamma. These parameters of a typical unit cell are shown in figure 1.6. Unit cells may be broadly divided into two categories, that is the primitive and centered unit cell. Primitive unit cells, when constant particles are present only on the corner portion of a unit cell, it is called the primitive unit cell. Centered unit cell, when a unit cell contains one or more constant particles present at positions other than corners in addition to those at corners, it is called a centered unit cell. Centered unit cells are of three types. Body centered unit cell. Such a unit cell contains one constant particles, i.e. atoms, molecules or ion, at its body center beside the ones that are at the corners. Face-centered unit cell. Such a unit cell contains one constant particle present at the center of each face, beside the ones that are at its corners. And centered unit cell. In such a unit cell, one constant particle is present at the center of any two opposite faces besides the one present at its corner. In all, there are 7 types of primitive unit cells. The characteristic along with the centered unit cell they can form have been listed in table 1.3. That is cubic, tetragonal, orthorhombic, hexagonal, rhombohedral or trigonal. Possible variations are cubic, primitive, body centered, face centered, where A is equal to B is equal to C, alpha equal to beta equal to gamma equal to 90 degree. Examples are NaCl, zinc blend, etc. Orthorhombic, that is primitive, body centered, face centered and centered. A is not equal to B, not equal to C. Alpha equal to beta equal to gamma equal to 90 degree. Rhombic sulfur, KNO3, barium sulfate. Hexagonal, there is a primitive, A equal to B, not equal to C. Alpha equal to beta equal to 90 degree, gamma equal to 120 degree. Graphite, zinc oxide, cadmium sulfide. Rhombohedral or trigonal, that is a primitive, A equal to B equal to C, alpha equal to beta equal to gamma not equal to 90, that is a calcite, calcium carbonate or cinnabar. Monoclinic, there is a primitive and centered, A is not equal to B not equal to C, alpha equal to gamma equal to 90 degree but beta is not equal to 90 degree, that is the monoclinic sulfur Na2SO4.10H2O. Triclinic, that is the primitive, A is not equal to B not equal to C, alpha is not equal to beta is not equal to gamma equal to not equal to 90 degree. Examples are K2Cr2O7, copper sulfate 5H2O, H3BO3, that is the boric acid. Now what are the numbers of atoms in a unit cell? We know that Any crystal lattice is made up of a very large number of unit cells, and the lattice point is occupied by one constant particle atoms. Let us now work out what portion of each particle belongs to a particular unit cell. We shall consider three types of cubic unit cells, and for simplicity assume that the constant particles is an atom. There is a primitive cubic unit cell. Primitive cubic unit cell has atoms only at its corners. Each atom at a corner is shared between 8 adjacent unit cells as shown in the figure. 4 unit cells in the same layer and 4 unit cells of the upper layer. Therefore, only 1/8 of an atom actually belong to a particular unit cell. In a primitive cubic unit cell has been depicted in 3 different ways. A small sphere occupying that position and not its actual size. Such structures are called open structures. The arrangement of particles is easier to follow in open structure. Depicts space-filling representation of the unit cell with actual particle size, and figure 1.9c shows the actual portions of the different atoms present in a cubic unit cell. In all, since each cubic unit cell has 8 atoms on its corners, the total number of atoms in one unit cell is 8 into 1 by 8 equal to 1 atom. Now, body-centered cubic unit cell. A body-centered cubic unit cell has an atom at each of its corners and also one atom at its body center. Open structure. B is space-filling model, and C is the unit cell with the portions of atoms actually belonging to it. It can be seen that the atom at the body center in the unit cell 8 into 1 by 8 equal to 1 atom. One body center equal to 1 atom. Total number of atoms per unit cell is equal to 2 atoms. Face-centered cubic unit cell. A face-centered cubic, that is the FCC unit cell, contain atoms at all of the corners and at the center of all the faces of the cube. It can be seen in figure 1.11 that each atom located at the face center is shared between 2 adjacent unit cells, and only half of each atom belongs to a unit cell. Open structure here depicted. Now we will study the closed packed structures. In solids, the constant particles are closed packed, leaving the minimum vacant space. Let us consider the constant particles at identical hard spheres and build up the 3-dimensional structure in 3 steps. A is the closed packing in 1 dimension. There is only one way of arranging spheres in 1-dimensional closed packed structure, that is to arrange them in a row and touching each other. In this arrangement, each sphere is in contact with 2 of its neighbors. The number of nearest neighbors of a particle is called its coordination number. Thus, in 1-dimensional closed packed arrangement, the coordination number is 2. Closed packing in 2 dimension. The 2-dimensional closed packing structure can be generated by stacking the rows of closed packed spheres. This can be done in 2 different ways. The second row may be placed in contact with the first one such that the spheres of the second row are exactly above those of the first row. The spheres of the 2 rows are aligned horizontally as well as vertically. If we call the row as A-type row, the second row being exactly the same as the first one is also of A-type. Similarly, we may place more rows to obtain AAA type of arrangement as shown in figure 1.14a. In this arrangement, each sphere is in contact with 4 of its neighbors, thus the dimensional coordination number is 4. Also, if the centers of these 4 immediate neighbors spheres are joined, a square is formed. Hence, this packing is called the square closed packing in 2 dimensions. The second row may be placed above the first one in staggered manner such that its sphere fit in the depressions of the first row. If the arrangement of spheres in the first row is called A-type, the one in the second row is different and may be called the B-type. When the third row is placed adjacent to the second in staggered manner, its spheres are aligned with those of the first layer. Hence, this layer is called also A-type. The spheres of similarly placed fourth row will be aligned with those of the second row. Hence, this arrangement is of AB type. In this arrangement, there is less free space and this packing is more efficient than the square closed packing. If the arrangement of sphere in the first row is A-type, the one in the second row is different and may be called as B-type. When the third row is placed adjacent to the second in staggered manner, Its spheres are aligned with those of the first layer, hence this layer is also of A type. The spheres of similarly placed fourth row will be aligned with those of second row, hence this arrangement is of AB type. In this arrangement there is less free space and this packing is more efficient than the square close packing. Each sphere is in contact with 6 of its neighbors and the two-dimensional coordination number is 6. The centers of these six spheres are at the corners of a regular hexagon. Hence, the packing is called two-dimensional hexagonal close packing. It can be seen in figure 1.14b that in this layer there are some voids. These are triangular in shape. The triangular voids are of two types. So that is uh, in the one the apex triangles are plotting upward and in the next layer downwards. Close packing in 3 dimension. All real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers are one above the other. In the last section we discussed close packing in 2 dimensions, which can be of two types: square close packed and hexagonal close packed. Let us see what type of 3-dimensional close packing can be obtained from these. 3-dimensional close packed form 2-dimensional square close packing layers. While placing the second square close packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically, as shown in figure 1.15. Similarly, we may place more layers one above the other if the arrangement of spheres in the first layer is called A type. All the layers are the same arrangement, thus the AA type pattern. The lattice thus generated is a simple cubic lattice and it is unit cell is the primitive cubic unit cell. 3-dimensional close packing form 2-dimensional hexagonal close packed layers. 3-dimensional close packed structures can be generated by placing layer one above the other. Thank you and have a nice day.